Hello everyone and welcome to this second lecture. That is Hello everyone and welcome to this third video on Perceptron. We'll see what a perceptron is and the learning rule. Okay, so the definition of a perceptron is it is a neural network that uses Maculoped's model and is capable of binary classification. Okay, so we have seen this Maculoped's model in the last video, and what this perceptron basically does is it uses that particular Maculoped's model and it is capable of doing binary classification. What is classification? Binary classification, just basically dividing the data into two. All right, so wherever we have to divide our data into two classes, say a message is spam, should go to a spam folder or not, if the image is of a dog or a cat or simple classifications, yes or no, 0 or 1s, is basically binary classification. Okay, so as you can see over here, the flow goes from MP, that is Maculoped's model, to perceptron, to multi-layer perceptron, and then finally the deep learning, um, more complicated networks. Okay, so the structure, it consists of inputs, weights, and a bias. All right, so this bias term was not actually present in the previous Maculoped's model. What the bias has been introduced over here. What the function of this bias is to, if there is a function that does not pass through the origin, then the bias is used to move our line, because perceptron, as it was the case with Maculoped's model, perceptron as well only works on linearly separable data. Okay, so since that is the case, uh, it could be that the linearly separable data, the line or the plane which separates the two datas, is does not pass through the origin. Okay, and to facilitate that, bias is introduced over here. Okay, it uses threshold activation function. So again, the threshold which we used in Maculoped's model is also used over here. Usually the threshold is set to 0. Okay, the perceptron calculates the weighted sum of the inputs and compares it with the threshold. The output is then 1 if the sum is greater than the threshold, otherwise it is 0. So since the input as well as the output to this perceptron is 0, so uh, whatever you get as the output will either be a 1 or a 0. Okay, this is the equation that goes up. Okay, first we calculate wi xi plus b, and if that is greater than, say, the threshold, which is 0 in this case, then we give the output as 1. If it is less than or equal to 0, then we give 0. Okay, so the weights, w are weights, x are input, and b is bias, as you can see over here. Again, I have basically perceptron, I kept the image same over here. Okay, just to signify that this is a single layer perceptron. Okay, it is a single layer, as it is with the neurons. All right, there was no real reason to keep it over here, other than uh, just to give you an analogy of the um, biological neuron being reflected over here. Okay, so this is how it is in case of single layer perceptron. Now we'll move on to looking at a solution. Okay, a solution for AND gate. All right, so we'll see how AND gate is solved by using this particular perceptron. Perceptron actually enables learning. Okay, learning, that is adjusting of weights and biases, is does happen in perceptron. Okay, I'm so sorry. Yeah. So since after this weights are we get the weights. Okay, we basically calculate if the current output that we got is equal to the output that was intended. If it is not the case, then we update the weights. Okay, and the updation process is basically done by something called as the delta rule. All right. So the delta rule, sorry, what we do basically is, for each training example we calculate the output using the current weights. The output is, if the output is correct, there is no change. If the output is incorrect, then we update the weights. Okay, and what the updation is given over here by delta rule. Okay, so for the weights, all right, just for the weights, it is neta into y minus y hat. Y hat is the predicted output, y is the actual output, into x for the weights. All right, and for the bias, it is b new, or b new is equal to b old plus neta into y minus y hat. All right, so basically if I had to get delta b, that would be this term, that is neta into y minus y hat. All right, so that we use in our perceptron, and then we calculate the errors. Okay, so calculate the errors and remove them. All right, so assume this scenario that initially the weights were 0 comma 0. Here it is shown as weights are 1, right? Okay, I'll use a different color basically. Yeah, here the weight is given as 1 for both, and bias is 1 minus 1.5. Assume that initially it was 0 comma 0. Okay, for each of them. All right, we started with weights 1 by weight 1 as 0, weight 2 as 0, and the bias as 0. Okay, then we calculated everything like in this order. Okay, everything was calculated in this order, and once we calculated everything, we did not get the actual output. So what did we do? We used the delta rule. Okay, and updated the weights. So weight was is equal to weight, old weight, plus and there was delta w. Okay, and what was that delta w? That delta w was equal to uh, y minus y hat multiplied by neta, which is the learning rate, and xi. Okay, so this was the term. I'm so sorry, I have scribbling over here, but I could have used a new one, but anyway. Okay, so this is the updation for weights, and for the bias it will be neta into b minus uh, the old weight, the y hat y hat y minus y hat, sorry, y minus y hat into neta. Okay, and into b, I guess, right? So that would be for bias. Right, now we come to this we come to a proof that this perceptron actually solves. Does it actually solve the uh, problem of XOR? Sorry, not XOR, AND. All right, to see that, what we are taking is we take this solution, we take this value which we know is the solution. Okay, so this is the truth table. Okay, the truth table of AND gate. All right, this is AND gate, And what we want is only when the inputs are 1 1, the output should be 1. Okay, so we have this our regular formula, right? Which is w1 x1 plus w2 x2 plus b, and if that is greater than or equal to 0, then we have 1. So it should be only greater than 0. I'm so sorry. Otherwise, it will be 0. Okay. So if it is equal to or less than 0, then it is 0. All right. The solution is w1 is equal to 1, w2 is equal to 1, and b is equal to minus 1. How did we come to these values? We ran those loops multiple times. Okay, but does this solve our equation? Let us see. Okay, so we took all those values over here, and we took the first input, which is w1 is equal to 0, w2 is equal to 0. We put all the values over here, we get this value, that is minus 1. Since minus 1 is less than 0, then what we do is we write y is equal to 1. Oh, sorry, y is equal to 0. Okay, so that was stated over here. Yes. Now, for the second one, we see the value again comes out to be minus 0.5, and hence, since this is less than 0, we have y is equal to 0. Okay. For the third case, for the third input, the x1 is equal to 1, x1, x2 is equal to 0. We check that the value is again minus 0.5, so y ends up to be 0. All right. And for the fourth one, uh, you'll see that since the output input is the x1 is equal to 1, x2 is equal to 1, we get the output as 0.5, and since it is greater than 0, our output y is 1. Okay, and now when we see all the four outputs, okay, so the first output that we got was 0, then the second one we got as 0, sorry, yeah, over here. Then the second one we got as 0, the third one we got as 0, and the fourth one we got as 1. All right. So this is exactly the output for the AND gate. All right. And this particularly shows how we can solve this problem using uh, a perceptron, a single layer perceptron. Now this is a linearly separable problem. We'll see what linearly separable problem is and how to solve a non-linear problem using multi-layer perceptron in the next video. Thank you very much.